All right. We've got just about every type of caffeination vehicle available to us for the reading of this 5th chapter of Rust for Rustaceans. Looks like we're going to go over project structure, which is super cool because this is the kind of thing that can really screw you if you don't know what you're doing like me and just realize that you've set yourself up for failure at the very beginning, especially if you're like working with a team and you just can't change anything. That's always annoying. So yeah, let's see. This chapter provides some ideas for structuring your Rust projects. For simple projects, the structure set up by cargo new is likely to be something you think little about. Yeah, that's one of the great things about Rust is you just do cargo new and it makes it for you. You may add some modules to split up the code and some dependencies for additional functionality, but that's about it. However, as a project grows in size and complexity, you'll find that you need to go beyond that. And maybe the compilation time for your crate is getting out of hand, or you need conditional dependencies, or you need a better strategy for continuous integration. In this chapter, we'll look at some of the tools the Rust language, and Cargo in particular, provide to make it easier to manage such things. And this is why it's cool, because it's so hard to guess exactly what your structure should look like at the very beginning. Features. Features are Rust's primary tool for customizing projects. At its core, a feature is just a build flag that crates can pass to their dependencies in order to add optional functionality. Features carry no semantic meaning in and of themselves. Instead, you choose what a feature means for your crate. Okay. Generally, we use features in 3 ways: to enable optional dependencies, to conditionally include additional components of a crate, and to augment the behavior of the code. Note that all of these are additive features, or are additive. Features can add to the functionality of the crate, but they shouldn't generally do things like remove modules or replace types or function signatures. This stems from the principle that if a developer makes a simple change to their cargo toml, such as adding a new dependency or enabling a feature, that shouldn't make their crates stop compiling. If a crate has mutually exclusive features, that principle quickly falls by the wayside. If crate A depends on one feature of crate C, and crate B on another mutually exclusive feature of C, adding a dependency on crate B would break crate A, right? For that reason, we generally follow the principle that if crate A compiles against crate C with some set of features, it should also compile if all features are enabled on crate C. Cargo leans into this principle quite hard. For example, if 2 crates A and B both depend on crate C, but they each enable different features on C, Cargo will compile crate C only once, with all the features that either A or B requires. That is, I'll take the union of the requested features for C across A and B. Because of this, it's generally hard to add mutually exclusive features to Rust crates. Chances are that some 2 dependents will depend on the crate with different features. And if those features are mutually exclusive, the downstream crate will fail to build. Note, I highly recommend that you configure your continuous integration infrastructure to check that your crate compiles for any combination of its features. One tool that helps you do this is Cargo Hack, which you can find here. Yeah, that sounds super useful. Got our espresso. Cheers. Defining and including features. Features are defined in cargo.toml. Listed 5.1 shows an example of a crate named foo with a simple feature that enables the optional dependency sync. I don't know how you pronounce this. Sin. Package foo, features. So this is optional. Derive equals sin. So, and then you add it to dependencies. See, I've done this. I've not done this, which is what he's talking about. Not with sin, of course. So that's an optional dependency. When cargo compiles this crate, it will not compile the sin crate by default, which reduces compile time, often significantly. The sin crate will be compiled only if a downstream crate needs to use the APIs enabled by the derived feature and explicitly opts into it. I wonder if that's how they like use stuff for testing. Something similar. Listing 5.2 shows how such a downstream crate bar would enable the derived feature and thus include the sin dependency. Okay, so this is like broken up across pages, which is annoying, but still, it's the same thing. Both this is derive. Yeah. So instead of doing features here, it does it here. Some features are used so frequently that it makes more sense to have a create opt out of them, rather than into them. To support this, Cargo allows you to define a set of default features for a crate. And similarly, it allows you to opt out of the default features of a dependency. Listing 5.3 shows how foo can make its derived feature enabled by default, while also opting out of some of Sync's default features and instead enabling only the ones it needs for the derived feature. Adding and opting out of default features in this optional dependencies. So let's see, derive and default. Dependencies.sync. Version 1, default features. So don't use the default features, use these features optionally. Okay. Chat setup. Chat. Okay. Here, if a crate depends on foo and does not explicitly opt out of the default features, it will also compile foo's sync dependency. Does not explicitly opt out of the default features, right? Like this. In turn, sync will be built with only the 3 listed features and no others. Opting out of default features this way and opting into only what you need is a great way to cut down your compile times. Yeah, so if you just know exactly what you're doing, you can cut down your compile time. Which is super helpful if you're doing a lot of iterations. Optional dependencies as features. When you define a feature, the list that follows the equal sign is itself a list of features. This might at first sound a little odd. In listing 5.3, sin is a dependency, not a feature. It turns out that Cargo makes every optional dependency a feature with the same name as the dependency. You'll see this if you try to add a feature with the same name as an optional dependency. Cargo won't allow it. Support for a different namespace for features and dependencies is in the works in Cargo, but has not been stabilized at the time of writing. In the meantime, if you want to have a feature named after a dependency, you can rename the dependency using package equals nothing. Oh, we've got a spammer. Block. How do I block? Boom. Wait. Remove. Okay, cool. So let's restart the sentence. In the meantime, if you want to have a feature named after a dependency, you can rename the dependency using blank. Oh, that's annoying. All right, I'm getting botted, I guess. Huh. How do I do this? I've never had to do this before. Remove. Report. Report. Nice. Okay. Hopefully that doesn't keep happening. So, in the meantime, if you want to have a feature named after a dependency, you can rename the dependency using package equals nothing to avoid the name collision. The list of features that a feature enables can also include features of dependencies. For example, you can write derive equals sin/derive to have your derive feature enable the derive feature of the sin dependency. Okay, so he's saying the equal sign is itself a list of features. When you define a feature, so he's saying this is a list of features, which makes sense. I think that's what he's saying. Okay, using features in your crate. When using features, you need to make sure your code uses a dependency only if it is available. And if your feature enables a particular component, you need to make sure that if the feature isn't enabled, the component is not included. You achieve this using conditional compilation, which lets you use annotations to give conditions under which a particular piece of code should or should not be compiled. Conditional compilation is primarily expressed using the #config attribute. There is also the closely related CFG bang macro, which lets you change runtime behavior based on similar conditions. You can do all sorts of neat things with conditional compilation, as we'll see later in this chapter, but the most basic form is #config feature equals some feature, which makes it so that the next thing in the source code is compiled only if the some feature is enabled. Similarly, if config bang feature equals some feature is equivalent to if true only if the derived feature is enabled and if false otherwise. Okay. The #config attribute is used more often than the config bang macro because the macro modifies runtime behavior based on the feature, which can make it difficult to ensure that features are additive. You can place #config in front of certain REST items, such as functions and type definitions, impl blocks, modules, and use statements, as well as on certain other constructs like struct fields, function arguments, and statements. The #config attribute can't go anywhere though. Where it can appear is carefully restricted by the Rust language team, so the conditional compilation can't cause situations that are too strange and hard to debug. Remember that modifying certain public parts of your API may inadvertently make a feature non-additive, which in turn may make it impossible for some users to compile your crate. You can often use the rules for backwards compatibility changes as a rule of thumb here. For example, if you make an enum variant or a public struct field conditional upon a feature, then that type must also be annotated with #non-exhaustive. Otherwise, a dependent crate that does not have the feature enabled may no longer compile if the feature is added due to some second crate in the dependency tree. Note: if you're writing a large crate where you expect that your users will need only a subset of the functionality, you should consider making it so that larger components, usually modules, are guarded by features. That way, users can opt into and pay compilation costs of only the parts they need. Okay, so this is cool. It's like not just project structure for you working in it or like your teammates working in it, but also for how the API is going to end up for sharing it, which is cool. Workspaces. This is the thing I don't know anything about, so it's cool. Crates play many roles in Rust. They are the vertices in the dependency graph, the boundaries for trait coherence, and the scopes for compilation features. Because of this, each crate is managed on a single compilation unit. The Rust compiler treats a crate more or less as one big source file, compiled as one chunk that is ultimately turned into a single binary output, either binary or a library. While this simplifies many aspects of the compiler, it also means that large crates can be painful to work with. If you change a unit test, a comment, or a type in one part of your application, the compiler must reevaluate the entire crate to determine what, if anything, changed. Internally, the compiler implements a number of mechanisms to speed up this process, like incremental recompilation or parallel code generation, but ultimately, the size of your crate is a big factor in how long your project takes to compile. For this reason, as your project grows, you may want to split it into multiple crates that internally depend on one another. Cargo is just the feature you need to make this convenient, or Cargo has just the feature you need to make this convenient. A workspace is a collection of crates, often called subcrates, that are tied together by a top-level Cargo TOML file, like the one shown in 5.4. So you can add these things. Okay, so like if your project is really big and you have multiple libs or something, you can add them to the workspace so that it takes advantage of some of these optimizations. This is like productivity hacks, which is sweet. The members array is a list of directives that each contain a crate in the workspace. Those crates all have their own cargo.toml files in their own subdirectories, but they share a common cargo log file in a single output directory. The crate names don't need to match the entry in members. It is common but not required that crates in a workspace share a name prefix, usually chosen as the name of the main crate. For example, in the Tokyo crate, the members are called Tokyo, Tokyo Test, Tokyo Macros, and so on. Perhaps the most important feature of workspaces is that you can interact with all of the workspace's members by invoking cargo in the root of the workspace. Want to check that they all compile? Cargo check will check them all. Want to run all your tests? Cargo test will test them all. It's not quite as convenient as having everything in one crate, so don't go splitting everything into minuscule crates, but it's a pretty good approximation. Okay. Cargo commands will generally do the right thing in a workspace. If you ever needed to disambiguate, such as if two workspace crates both have a binary by the same name, use the -p flag for package. If you are in the subdirectory for a particular workspace crate, you can pass --workspace to perform the command for the entire workspace instead. Once you have a workspace level cargo toml with the array of workspace members, you can set your crates to depend on one another using path dependencies, as shown in listing 5.5. You can set them as path dependencies. Interesting. So you can pick and choose what you want, so it gets smaller, like he was saying before. Interesting. Intercrate dependencies among workspace crates. Yeah. Interesting that you list these differently, both under the dependencies header. Now, if you make a change to the crate in bar 2, then only that crate is recompiled. Since foo in bar 1 did not change, it may even be faster to compile your project from scratch, since the compiler does not need to evaluate your entire project source for optimization opportunities. Right. Interesting. Specifying intra-workspace dependencies. The most obvious way to specify that one crate in a workspace depends on another is to use the path specifier, as shown in listing 5.5, However, if your individual subcrates are intended for public consumption, you may want to use version specifiers instead. Say you have a crate that depends on a get version of the one crate from the bar workspace in listing 5.5 with 1 equals get equals something, and a released version of foo also from bar with foo equals 1.0, Cargo will dutifully fetch the one get repository, which holds the entire bar workspace, and see that 1 in turn depends on foo, located at 2 directories down foo. Instead, the workspace, or inside the workspace, but Cargo doesn't know that the release version foo equals 1, and the foo and the get repository are the same crate. It considers the 2 separate dependencies that just happen to have the same name. Yeah. You already see where this is going. If you try to use any type from foo 1.0 with an API for one that accepts a type from foo, the compiler will reject the code. Yeah, that would be super hard to debug, I would think. But Rust probably has great messages for you for that, which is fantastic. Even though the types have the same name, the compiler can't know that they are the same underlying type. And the user will be thoroughly confused since the compiler will say something like expected foo type got foo type. Yeah. The best way to mitigate this problem is to use path dependencies between subcrates, only if they depend on published changes. Actually, maybe the compiler won't warn you, because that's what he's saying, is the compiler can't tell. If the compiler could tell, it would just fix it, probably. As long as one works with foo 1.0, it should list foo equals 1.0 in its dependencies. Only if you make a change to foo that one needs should you change 1 to use a path dependency. And once you release a new version of foo that one can depend on, you should remove the path dependency again. This approach also has its shortcomings. Now, if you change foo and then run the test for 1, you'll see that 1 will be tested using the old foo, which may not be what you expected. You'll probably want to configure your continuous integration infrastructure to test each subcrate, both with the latest release versions of the other subcrates, and with all of them configured to use path dependencies. Okay. So, yeah, no. There's not many people here, so if you're watching this, you're watching a VOD, and I thank you. Welcome to the channel. Project configuration. Running cargo new sets you up with a minimal cargo toml that has the crate's name, its version number, and some author information, and an empty list of dependencies. That will take you pretty far, but as your project matures, there are a number of useful things you may want to add to your cargo. Yeah, I remember when I first figured out you could like keep adding to that, I was like, oh man, this is just stuff that you just always use, so they add it automatically. Crate metadata. The first and most obvious thing to add to your cargo toml is all the metadata directives that cargo supports. In addition to obvious fields like description and homepage, it can be useful to include information such as the path to a README for the crate, the default binary to run with cargo run, and additional keywords and categories to help crate.io categorize your crate. For crates with more convoluted project layout, it's also useful to set include and exclude metadata fields. These dictate which files should be included and published in your package. By default, Cargo includes all files in a crate's directory except any listed in your gitignore file. But this may not be what you want if you have large text fixtures, unrelated scripts, or other auxiliary data in the same dictionary that you do want under version control. As their name suggests, include and exclude allow you to include only a specific set of files and exclude matching and exclude files matching a given set of parameters, respectively. So, if you have a crate that should never be published or should be published only to certain alternative registries, that is, not to crates.io, you can set the publish directive to false or to a list of allowed registries. Okay. The list of metadata directives you can use continues to grow, so make sure periodical checks on the manifest format page of the cargo reference. Oh, interesting. Build configuration. Cargo toml can completely custom build program for your crate. We'll revisit this in chapter 11. However, Cargo also provides two smaller but very useful mechanisms that we'll explore here: patches and profiles. Patch. Okay. The patch section of Cargo toml allows you to specify a different source for a dependency that you can use temporarily, no matter where in your dependencies the patch dependency appears. This is invaluable when you need to compile your crate against a modified version of some transitive dependency to test a bug fix, performance improvement, or a new minor release you're about to publish. Listing 5.6 shows an example of how you might temporarily use a variant of a set of dependencies. So this is like if you do like a fork or something. Interesting. Patch a get dependency. So he's talking about this and this. Overriding a dependency source in Cargo toml with a patch. Even if you patch a dependency, Cargo takes care to check the crate versions so that you don't accidentally end up patching the wrong major version of a crate. If you, for some reason, transitively depend on multiple major versions of the same crate, you can patch each one by giving them distinct identifiers in 5.7. So you can just name them separately, I guess. That's cool. Overwriting multiple versions of the same crate using patch. Cool. Cargo will look at the cargo toml inside each path and realize that nom4 contains major version 4 and that nom5 contains major version 5. Patch the two versions appropriately. The package keyword tells Cargo to look for a crate by the name nom in both cases instead of using the dependency identifiers, the part on the left as it does by default. You can use package this way in your regular dependencies as well as to rename a dependency. Keep in mind that patches are not taken into account in the package. Patches are not taken into account in the package. That's uploaded when you publish a crate. A crate that depends on your crate will use only its own patch section, which may be empty, not that of your crate. Yeah, that would be rough. Crates versus packages. So you may wonder what the difference between a package and a crate is. These two terms are often used interchangeably in an informal context, but they also have specific definitions that vary depending on whether you're talking about the Rust compiler, Cargo, crates.io, or something else. I personally think of a crate as a Rust module hierarchy, starting at a root.rs file, one where you can use crate level attributes like hashbang feature, usually something like lib.rs or main.rs. In contrast, a package is a collection of crates and metadata. So essentially all that's described by a cargo.toml file that may include a library crate, multiple binary crates, some integration test crates, and maybe even multiple workspace members that themselves have cargo.toml files. Okay, Now we're going to talk about profile. The profile section lets you pass additional options to the Rust compiler in order to change the way it compiles your crate. These options fall primarily into three categories: performance options, debugger options, and options that change your code behavior in user-defined ways. They all have different defaults depending on whether you are compiling in debug mode or in release mode. Other modes also exist. The three primary performance options are opt level, code gen units, and LTO. The opt level option tweaks runtime performance by telling the compiler how aggressively to optimize your program. 0 is not at all, 3 is as much as you can. Oh yeah, I think I remember something like this in the Rust book. The higher the setting, the more optimized your code will be, which may make it run faster. Extra optimization comes at the cost of higher compile times, though, which is why optimizations are generally enabled only for release builds. You can also set opt level to S to optimize for binary size, which may be important on embedded platforms. So this is like small. I'm excited to look at embedded stuff. If you have any suggestions for that, let me know in the comments. That's a whole nother journey. The code gen units option is about compile time performance. It tells the compiler how much independent compilation tasks, code generation units, it is allowed to split the compilation of a single crate into. The more pieces a large crate's compilation is split into, the faster it will compile, since more threads can help compile the crate in parallel. Unfortunately, to achieve this speed up, the threads need to work more or less independently, which means code optimization suffers. Imagine, for example, that the segment of a crate compiling in one thread could benefit from inlining some code in a different segment. Since the two segments are independent, that inlining can't happen. This setting then is a trade-off between compile time performance and runtime performance. By default, Rust uses an effectively unbounded number of code degen units in debug mode. Basically, compile as fast as you can in a smaller number, 16 at the time of writing, in release mode. Okay. The LTO setting toggles link time optimization, which enables the compiler or the linker, if you want to get technical about it, to jointly optimize bits of your program known as compilation units that were originally compiled separately. The exact details of link time optimization are beyond the scope of this book, but the basic idea is that the output from each compilation unit includes information about code that went into that unit. After all, the units have been compiled, the linker makes another pass over all the units and uses that additional information to optimize the combined compiled code. This extra pass adds to the compile time but recovers most of the runtime performance that may have been lost due to splitting the compilation into smaller parts. In particular, the LTO can offer significant performance boosts to performance-sensitive programs that might benefit from cross-compilation. Be aware, though, that cross-crate LTO may add a lot to your compile time. Oh, this person's back. I guess I'm gonna have to delete the chat from the VOD. Report. Okay. This is not the same person. Okay. That's annoying. I wonder why I'm getting that all of a sudden. Do I not have mods? Is Nightbot not here? Where's Nightbot? 1 second. Oh. Am I on? Okay, yeah. Why isn't Nightbot catching them? We'll see. We'll see if Nightbot does anything. Okay. Add a lot to your okay. Rust performs link time optimization. Pro tip: acronyms like this are really just for text, so you should always say them out so that you remember them and know what you're talking about. Between computer science and healthcare, there's so many acronyms, it's insane. And there's a lot of overlap. Like LTO could mean something else. Rust performs link time optimization across all the code degen units within each crate by default in an attempt to make up for the lost optimizations caused by using many codegen units. Since link time optimization is performed only within each crate rather than across crates, this extra pass isn't too onerous, and the added compile time should be lower than the amount of time saved by using a lot of codegen units. Rust also offers a technique known as thin link time optimization, which allows the LTO pass to be mostly parallelized at the cost of missing some optimizations a full link time optimization pass would have found. Link time optimization can be used to optimize across foreign function interface boundaries. Ooh, that's interesting. Like iOS apps and LTO and just like adding to like build on Python or something. I think that's what that means. See the linker plugin LTO rustc flag for more details. Cool. The profile section also supports flags that aid in debugging, such as debug assertions, and overflow checks. The debug flag tells the compiler to include debug symbols in the compiled binary. This increases the binary size, but it means that you get function names and such, rather than just instruction addresses in backtraces and profiles. The debug assertions flag enables the debug assert macro and other related debug code that isn't compiled otherwise through config debug assertions. Such code may make your program run slower, but it makes it easier to catch questionable behavior at runtime. The overflow checks flag, as the name implies, enables overflow checks on integer operations. This slows them down, notice a trend here, but can help you catch tricky bugs early on. By default, these are all enabled in debug mode and disabled in release mode. Interesting. Let me just check on Nightbot real quick. Commands. Yeah, so let's just have it under this. Let's see. See if Nightbot catches anything. Or is even in the chat. Profile star panic. The profile section has another flag that deserves its own subsection, panic. This option dictates what happens when code in your program calls panic, either directly or indirectly through something like unwrap. You can set panic to either unwind, the default on most platforms, or abort. We'll talk more about panics and unwinding in chapter 9, but I'll give a quick summary here. Okay, Nightbot is here. Also, that's my Twitter, if you want to check me out. Starts. Okay, so normally in Rust, when your program panics, the threads that panicked starts unwinding its stack. You can think of unwinding as forcibly returning recursively from the current function all the way to the bottom of that thread stack. That is, if main called foo, food called bar, and bar called baz, a panic in baz would forcibly return baz, then bar, then foo, and finally from main, resulting in the program exiting. A thread that unwinds will drop all values on the stack normally. which gives the values a chance to clean up resources, report errors, and so on. This gives the running system a chance to exit gracefully, even in the case of a panic. When a thread panics and unwinds, other threads continue running, unaffected. Only when and if the thread that ran main exits does the program terminate. That is, the panic is generally isolated to the thread in which panic occurred. This means unwinding is a double-edged sword. The program is limping along with some failed components, which may cause all sorts of strange behaviors. For example, imagine a thread that panics halfway through updating the state in a mutex. Any thread that subsequently acquires that mutex must now be prepared to handle the fact that the state may be in partially updated inconsistent state. For this reason, some synchronization primitives, like mutex, will remember if a panic occurred when they were last accessed, and communicate that to any thread that tries to access the primitives subsequently. If a thread encounters such a state, it will normally also panic, which leads to a cascade that eventually terminates the entire program. But that is arguably better than continuing to run with corrupted state. The bookkeeping needed to support unwinding is not free, and it often requires special support by the compiler and the target platform. For example, many embedded platforms cannot unwind the stack efficiently at all. Rust therefore supports a different panic mode. Abort ensures the whole program simply exits immediately when a panic occurs. In this mode, no threads get to do any cleanup. This may seem severe, and it is, but ensures that the program is never running in a half-working state and that errors are made visible immediately. The panic setting is global. If you set it to abort, all your dependencies are compiled with abort. That when a thread panics, it tends to print a backtrace. The trail function calls it led you to where the panic occurred. This is also a form of unwinding, though it is separate from the unwinding panic behavior discussed here. You can have backtraces even with panic equals abort by passing C-force unwinding tables to rustc, which makes rustc include the information necessary to walk back up the stack while terminating the program on a panic. Okay. Profile overrides. You can set profile options for just a particular dependency or a particular profile using profile overrides. For example, listing 5.8 shows how to enable aggressive optimizations for the Serde crate and moderate optimizations for all other crates in debug mode using the profile name, package, crate name syntax. Okay. So you can specify which optimization level each one is brought in at. Interesting. So you can sort of targetedly optimize your compile times. This kind of optimization override can be handy if some dependency would be prohibitively slow in debug mode, such as decompression or video encoding, and you need it optimized so that your test suite won't take several days to complete. You can also specify global profile defaults using a profile.dev, similar section in the cargo configuration file in root cargo config. When you set optimization parameters for a specific dependency, keep in mind that the parameters apply only to code compiled as part of that crate. If Serde, in this example, has a generic method or type that you use in your crate, the code of that method or type will be monomorphized and optimized in your crate, and your crate's profile settings will apply, not those in the profile override for Serde. Interesting. Conditional compilation. Most Rust code you write is universal. It'll work the same regardless of what CPU or operating system it runs on. But sometimes, you'll have to do something special to get the code to work on Windows, on ARM chips, or when compiled against a particular platform application binary interface, or ABI. ABI, not API, obviously. Or maybe you want to write an optimized version of a particular function when a given CPU instruction is available. Interesting. Or disable some slow but uninterested setup code when running in a continuous integration environment. To cater to cases like these, Rust provides mechanisms for conditional compilation in which a particular segment of code is compiled only if certain conditions are true of the compilation environment. We denote conditional compilation with the config keyword, as you saw earlier in the chapter, using features in your crate. It usually appears in the form #config condition attribute, which says to compile the next item only if condition is true. Rust also has #config attribute condition attribute, which is compiled as #attribute if condition holds and is a no-op otherwise. You can also evaluate a config condition as a Boolean expression using the config bang condition macro. Every config construct takes a single condition made up of options like feature equals some feature, and the combinators all, any, and not, which do what you would probably expect. Options are either simple names like Unix or key value pairs like those used by feature conditions. There are a number of interesting options you can make completion dependent on. Let's go through them from most common to least common. Okay. This is pretty neat stuff. Really holding true to the picking up where the book left off mantra. So, feature options. You've already seen examples of these. Feature options take the form feature equals name of feature and are considered true if the named feature is enabled. You can check for multiple features in a single condition using the combinators. For example, any feature equals F1 and feature equals F2 is true if either feature F1 or F2 is enabled. Okay. Operating system options. These use key value syntax with the key target OS and values like Windows, Mac OS, Linux. You can also specify a family of operating systems using target family, which makes the value Windows or Unix. These are common enough that they have received their own named short forms, so you can use config Windows and config Unix directly. For example, if you wanted a particular code segment to be compiled with only Mac OS and Windows, you can write #config any Windows target equals Mac OS. Ooh, this is cool too. I think I saw someone on Twitter show that you can use this in match statements. So it's like, if you're on this OS, execute this, and if you're on this OS, execute this. I don't know where that would be different, but apparently you can do that. Context options. These let you tailor code to a particular compilation context. The most common of these is the test option, which is true only when the crate is compiled under the test profile. Keep in mind that test is set only for the crate that is being tested, not for any of its dependencies. This also means that test is not set in your crate when running integration tests. It's the integration tests that are compiled under the test profile, whereas your actual crate is compiled normally. That is without test set. The same applies to the doc and doc test options, which are set only when building documentation or compiling doc test respectively. There's also the debug assertions option, which is set in debug mode by default. Tool options. Some tools like Clippy and Mira. I haven't seen this one, but Clippy's super great. set custom options, more on that later, and that let you customize compilation when run under these tools. Usually, these options are named after the tool in question. For example, if you want a particular compute-intensive test not to run under MIRI, you can give it the attribute config attribute MIRI ignore. So basically, you can turn on and off everything. Everything is probably too inclusive, since it's the most inclusive thing, but you get the idea. Architecture options. These let you compile based on the CPU instruction set the compiler is targeting. You can specify a particular architecture with target arc, which takes values like x86, MIPS, AArch64, or you can specify a particular platform feature with target feature, which takes values like AVX or SSE2 for very low-level code. You may also find that target endian and target pointer with options useful. Compiler options. These let you adopt your code to the platform ABI. It is also compiled against and are available through target environment with values like new, MSVC, and MUSL. For historical reasons, this value is often empty, especially on new platforms. You normally need this option only if you need to interface directly with an environment ABI, such as when linking against an ABI-specific symbol name using #link. While config conditions are usually used to customize code, some can only be used to customize dependencies. For example, the dependency WinRT usually makes sense only on Windows, and the Nix crate is probably useful only on Unix-based platforms. Listing 5.9 gives an example of how you can use config conditions for this. Okay, yeah, so you can say you can compile them separately based on what operating system you're using. That's cool. Here we specify that, let's get it in frame. Here we specify that WinRT version 0.7 should be considered a dependency only under config Windows, so on Windows, and Nix version on 0.17 only under config Unix, so on Linux, macOS, and other Unix-based platforms. One thing to keep in mind is that the dependencies section is evaluated very early in the process when only certain config options are available. In particular, feature and context options are not yet available at this point. So you cannot use this syntax to pull in dependencies based on features and contexts. You can, however, use any config that depends only on the target specification or architecture, as well as any options explicitly set by tools that call into Rust-C, like config MIRI. Oh, hey Carlos. Thanks for stopping by. I'm glad you like it. It's a super good book. Note, while we're on the topic of dependency specifications, I highly recommend that you set up your CI infrastructure to perform basic auditing of your dependencies tools, like cargo deny and cargo audit. These tools will detect cases where you transitively depend on multiple major versions of a given dependency, where you depend on crates that are unmaintained or have known security vulnerabilities, or where you use licenses that you may want to avoid. Using such a tool is a great way to raise the quality of your codebase in an automated way. Yeah, I have a lot to learn about CI infrastructure. Hopefully soon. It's also quite simple to add your own custom conditional compilation options. That's a tongue twister. You just have to make sure that config my option is passed to Rust-C when Rust-C compiles your crate. The easiest way to do this is to add your config to the Rust flags environment variable. This can come in handy in CI, where you may want to customize your test suite depending on whether it's being run on CI or on a dev machine. add config equals CI to Rust flags in your CI setup, and then use config CI and config not CI in your code. Options set this way are also available in your cargo dependencies. That's interesting. Like, one of the worst parts of Rust is all Rust crates are versioned and are expected to follow cargo's implementation of semantic versioning. Semantic versioning dictates the rules for what kinds of changes require what kinds of version increases, and for which versions are considered compatible, and in what ways. The RFC 1105 standard itself is well worth reading. It's not horribly technical, but to summarize, it differentiates between three kinds of changes: breaking changes, which require a major version change; additions, which require a minor version change; and bug fixes, which require only a patch version change. RFC 1105 does a decent job of outlining what constitutes a breaking change in Rust, and we've touched on some aspects of it elsewhere in this book. I won't go into detail here, but about the exact semantics of the different types of changes. Instead, I want to highlight some less straightforward ways version numbers come up in the Rust ecosystem, which you may need to keep in mind when deciding how to version your own crates. So if you're making your own thing, you sort of need to know this, which is kind of the whole point. So, minimum supported Rust version. The first Rustism is the minimum supported Rust version, MSRV. Okay. There's much debate in the Rust community about what policy projects should adhere to when it comes to their minimum supported Rust version and versioning. And there's no truly good answer. The core of the problem is that some Rust users are limited to using older versions of Rust, often in an enterprise setting where they have little choice. If we constantly take advantage of newly stabilized APIs, those users will not be able to compile the latest versions of our crates and will be left behind. There are two techniques crate authors use to make life a little easier for users in this position. The first is to establish an MSRV policy promising that new versions of a crate will always compile with any stable release from the last X months. The exact number varies, but 6 or 12 months is common. With Rust's 6-week release cycle, that corresponds to the latest 4 or 8 stable releases, respectively. Any new code introduced in a project must compile with the MSRV compiler, usually checked by CI, or be held until the MSRV policy allows it to be merged as is. This can sometimes be a pain, as it means that crates cannot take advantage of the latest and greatest language has to offer, but it will make life easier for your users. The second technique is to make sure the minor version number of your crate to increase the minor version of your crate anytime that the MSRV changes. So, if you release a version 2.7.0 of your crate, and that increases your MSRV from Rust 1.44 to Rust 1.45, then a project that is stuck on 1.44 and that depends on your crate can use the dependency version specifier equals 2 and then less than 2.7 to keep that project working until it can move on to Rust 1.45. It's important that you increment the minor version, not just the patch version, so that you can still issue critical security fixes for the previous MSRV release by doing another patch release if necessary. Oh, that's cool. So he's basically saying, like, changing your MSRV is a bug fix, or not a bug fix, but like a version change. That way you can do bug fixes on the previous version and the new version. Some projects take their MSRV support so seriously that they consider an MSRV change a breaking change and increment the major version number. This means that downstream projects will explicitly have to opt into an MSRV change rather than opting out. but it also means that users who do not have such strict MSRV requirements will not see future bug fixes without updating their dependencies, which may require them to issue a breaking change as well. As I said, none of these solutions are without drawbacks. Enforcing an MSRV in the Rust ecosystem today is challenging. Only a small subset of crates provide an MSRV guarantees, and even if your dependencies do, you will need to constantly monitor them to know when they increase their MSRV. When they do, you'll need to do a new release of your crate with the restricted version bounds mentioned previously to make sure your MSRV doesn't also change. This may in turn force you to forego security and performance updates made to your dependencies, as you'll have to continue using older versions until your MSRV policy permits updating. And that decision also carries over to your dependents. There have been many proposals to build MSRV changes or checking into cargo itself, but nothing workable has been stabilized as of this writing. See, that's the cool thing, is Rust handles so many things that every language has to deal with this, but Rust, I don't know how they manage it. Rust clears away so many other things that you would worry about first. So we can get to these really hairy problems. Minimal dependency versions. When you first add a dependency, it's not always clear that what version specifier you should give that dependency. Programmers commonly use the latest version or just the current major version. But chances are that both of these choices are wrong. By wrong, I don't mean that your crate won't compile, but rather that making the choice may cause strife for users of your crate down the line. Let's look at why each of these cases is problematic. First, consider the case where you add a dependency on hugs equals 1.7.3, the latest published version. Now imagine that a developer somewhere depends on your crate, but they also depend on some other crate foo that itself depends on hugs. Further, imagine that the author of foo is really careful about their MSRV policy, so they depend on hugs equals 1 less than 1.6. Here, you'll run into trouble. Where cargo sees hug equals 1.7.3, it considers only versions greater than or equal to 1.7. But then it sees that foo's dependencies on hugs require less than 1.6, so it gives up and reports that there is no version of hug compatible with the requirements. Sounds like a problem. In practice, there are a number of reasons why a crate may explicitly not want a newer version of a dependency. The most common ones are to enforce MSRV to meet enterprise auditing requirements. Fair. The newer version will contain code that hasn't been audited, and to ensure reproducible builds that are only the exact listed version is used. This is unfortunate, as it could well be that your crate compiles fine with, say, hugs 1.56. Maybe it even compiles fine with any 1.x version. But using the latest version number, you're telling cargo to consider only versions at or beyond the minor version. In this solution, is the solution to use hugs equals 1 instead then? No, it's not quite right either. It could be that your code truly depends on something that was added only in hugs 1.6. So while 1.6.2 would be fine, 1.5.6 would not be. Ugh. You wouldn't notice this if you were only ever compiling your crate in situations where a newer version ends up getting used. But if some crate in the dependency graph specifies hugs equals 1 less than 1.5, your crate would not compile. Man, this is gnarly. The right strategy is to list the earliest version that has all the things your crate depends on, and to make sure that this remains the case even as you add new code to your crate. But how do you establish that beyond trawling the changelogs or trial and error? Your best bet is to use Cargo's unstable z minimal versions flag, which makes your crate use the minimal acceptable versions for all dependencies rather than the maximum. Interesting. And Cargo's so great. Then set up all your dependencies to just the latest major version number. Try to compile and add a minor version to any dependencies that don't. Rinse and repeat until everything compiles fine, and you now have your minimum version requirements. Man, Jon's so smart. All these little things you gotta learn about. It's worth noting that while, like with MSRV, minimal version checking faces an ecosystem adoption problem. Minimum version checking faces an ecosystem adoption problem. While you may have set all your version specifiers correctly, the projects you depend on have not, or may not have. This makes the cargo minimal version flag hard to use in practice, and why it's still unstable. Okay. If you depend on foo, and foo depends on bar, with a specifier of bar equals 1, and it actually requires bar equals 1.4. Cargo will report that it failed to compile foo no matter how you list foo, because the Z flag tells it to always prefer minimal versions. You can work around this by listing bar directly in your dependencies with the appropriate version requirement. So if you isolate it, you can just make it explicit. But these workarounds can be painful to set up and maintain, yeah. You may end up listing a large number of dependencies that are only really pulled in through your transitive dependencies, and then you'll have to keep that list up to date as time goes on. Yeah, so like make your APIs properly so that you don't create a bunch of pain down the road, which would probably just result in your libraries not being used, which would suck. So note, one current proposal is to present a flag that favors minimal versions for the current crate, but maximal ones for dependencies, which seems quite promising. Nice. Changelogs. For all but the most trivial crates, I highly recommend keeping a changelog. There is little more frustrating than seeing that a dependency has received a major version bump and then have to dig through the git logs to figure out what changed and how to update your code. I recommend that you do not dump your git logs into a file named changelog, but instead keep a manual changelog. It is much more likely to be useful. A simple good format for changelogs is the keep a changelog format documented at keepachangelog.com. Cool. Unreleased versions. Rust considers version numbers even when the source of a dependency is a directory or a Git repository. This means that semantic versioning is important even when you have not yet published a release to crates.io. It matters what version is listed in your cargo toml between releases. The semantic versioning standard does not dictate how to handle this case, but I'll provide a workflow that works decently well without being too onerous. After you've published a release, immediately update the version number in your cargo.toml to the next patch version with a suffix like alpha1. If you just released 2.0.3, make the new version 2.0.4-alpha.1. You just released an alpha, increment the alpha number instead. Okay. As you make changes to the code between releases, keep an eye out for additive or breaking changes. If one happens and the corresponding version number has not changed since the last release, increment it. For example, if the last release version is 2.0.3, the current version is 2.0.4-alpha.2, and you make an additive change, make the version with the change 2.1.0 alpha.1. If you make a breaking change, it becomes 3.0 alpha.1 instead. If the corresponding version increase has already been made, just increment the alpha number. Okay. When you make a release, remove the suffix unless you want to do a pre-release, then publish and start from the top. This process is effective because it makes two common workflows work much better. First, imagine that a developer depends on major version 2 of your crate, but they need a feature that's currently available only in Git. Then you commit a breaking change. If you don't increase your major version at the same time, their code will suddenly fail in unexpected ways. Okay, yeah, so be nice to your people. Either by failing to compile or as a result of weird runtime issues. If you follow the procedure laid out here, you'll instead be notified by Cargo that a breaking change has occurred, and they'll have to either resolve that or pin a specific comment. Next, imagine that a developer needs a feature they just contributed to your crate, but which isn't part of any release version of your crate. They've used your crate behind a Git dependency for a while, so other developers on their project already have older checkouts of your crate's repository. If you do not increment the major version number in Git, this developer has no way to communicate that their project now relies on the feature that was just merged. If they push their change, their fellow developers will find that the project no longer compiles, since Cargo will reuse the old checkout. If, on the other hand, the developer can increment the minor version number for the Git dependency, then Cargo will realize that the old checkout is outdated. Interesting. This workflow is by no means perfect. It doesn't provide a good way to communicate multiple minor or major changes between releases, and you still need to do a little bit of work to keep track of the versions. However, it does address two of the most common issues Rust developers run into when they work against Git dependencies. And even if you make multiple changes between releases, this workflow will still catch many of the issues. If you're not too worried about small consecutive version numbers in releases, you can improve the suggested workflow by simply always incrementing the appropriate part of your version number. Be aware, though, that depending on how frequently you make such changes, this may make your version numbers quite large. Yeah, that seems really important for like if you're getting something up and running for like the initial users, like the very first users, or just for those people that like love to have the bleeding edge version. Like being nice to those core people is probably a really good idea. So summary, if you made it this far, you're my favorite person because this was a long chapter. But so summary. In this chapter, we've looked at a number of mechanisms for configuring, organizing, and publishing crates for both your own benefit and that of others. We've also gone over some common gotchas when working with dependencies and features in Cargo that now hopefully won't catch you out in the future. Catch you out. It's not. Anyway, in the next chapter, we'll turn to testing and dig into how you go beyond Rust's simple hash test functions that we know and love. Ooh, I love testing. Tests and like continuous integration are just great time savers. Anyways, that was chapter 5. Thank you for sticking around, and come back next week for chapter 6. Like, comment, subscribe, all that stuff. Anyways, I will see you next week. Have a good one.